Hello, good morning, everyone. Today we're going to be talking in our brand new episode of Black Bloody Engineering about a specific component. So, last time we tried to build the program counter, and today we're going to tie it up the data memory. This data memory is where your CPU actually remember things. Like, for example, when you're coding in C++ or Python, you usually define variables. And this is where temporary results and stack frame. This is the place where a bunch of calculations happen and they vanish instantaneously. It's not like your register in your register file where things are a little more permanent, but today we're gonna dive into the data memory and we're gonna be building it up. We start by showing you how data memory really works at the digital logic level. We're talking about deep flip-flops, three-state buffers, and address decoding. This is to simulate the actual hardware. This gives you a clear understanding of what is happening under the hood, something you won't get if I just drag and drop a RAM block, because Logisim do have RAM blocks, and if I just drop a component, then you don't see how it really works. Once you understand the theory, we'll switch to Logisim, and we can then go ahead build it with a RAM component. This is to allow us to make the things more scalable and more practical for our full MIPS CPU design. So guys, or gals, so whether you are an engineering student, a digital logic hobbyist, or someone who wants to build a CPU from scratch, you're going to walk away from this episode with a deep understanding of how modern processors load and store data. So for the purpose of this video, I'll be explaining what is data memory. The data memory is usually used to store runtime data, not instructions. Remember, our instructions are stored at the instruction memory, and this is where the program is loaded. So our data memory is our temporary memory. It's like your short-term memory. So when we're talking about the MIPS CPU, the data memory has the same as your ROM. It has an address, location, it has the data you want to write, the data that you want to write in here. It has an output as well. It has a write enable, and it also have a read enable. And this is gonna be your data memory. So how exactly are we gonna be building this? So like last time, we used the flip-flops. So let's see if we can do one real quick. So I have one flip-flop, two flip-flops, three, four, and then we have a D and a Q, a D and a Q, a D and a Q. We also need a clock because we have to clock the flip-flops. And we also need the enable signal. This is to write into them. And then it has the input, the output, the input, and the output. And then I guess we can copy this. We can copy this for our address 1, address 2. So we can say that we have is a the data input is going to be the same for all of them. And this is a bus of 4 bits. So there's 4 wires on that bus. And I guess we can connect all of them. Then we can have a tri-state buffer here with an enable signal here. We can have a decoder here. Yeah, that sounds right. A decoder. And we're gonna have the address, the operation here, and then I'm gonna have 3 wires here. This one can go here. This one can go here. This one can go here. That's my output. So I'll make this into a bus. So really you have 4 buffers here. You have the closed signal. They're all common to each other. Clock signal. And then I have a write enable signal. Let me change the color so you can see it better. That one can go. So the signal can go to all of them. And this will be your RAM internally. And this could be your address. And then this can have a memory read to enable the outputs. so the buffer can transfer this data to the other side. This will keep that my data bus, this is the data bus, my 4-bit data bus. It will keep it that only one of them can talk. So for example, if I have 001, then this is transferring this data here, and the other ones are in high impedance. So there's no conflict of outputs between all three. Okay, so now that I have explained how to build the RAM, we're gonna go ahead and try to implement our design. And the way we're gonna do it is with 4 deep flip-flops. And then we're gonna use splitters for the inputs. We're gonna use another splitter for the output. We're gonna use the buffer, control the output of the system, just like we have here. So we can share the same bus. And then all we have to do is we don't have an enable switch, so we might have to use an AND gate to implement that. This is gonna be our enable, or write enable. We can clock that signal with our clock. This is gonna be our data. This is gonna be our read or output. This is gonna get tied here. We can use a decoder to gate this too. This can be our re-enable. This can be our address. And if we clock this, doesn't have anything in here. But when I put some value in here, so I see that right now it's copying to all of them at the same time. So we'll fix that. That's a mistake. So if I put one and then re-enable, it outputs the one. But I'm unable to write to separate addresses at the same time. So one way we can fix that is by removing this line, copying this AND gate, we'll put it here. We can make this a 3 input. This one here, fuck that one. This will enable a separate register depending which one I want. If I disable that, it stays. And if I change the address and serialize it, it'll serialize at one at a time. The problem with this system that I have right now is that if I disable the read enable, then I'm unable to write to address number 1 because this is disabled. If you can see, it will only write when I hit read enable. So we gotta fix that. A way that we can fix that is probably do some changes to the way we have this implemented. So right now, we can clean up this a little bit. Right now we have 2 buffers here, but in reality, we always output into a line where I don't need information. So if I remove these 2 values, those 2 buffers from there, I'll replace that with a multiplexer. I can put that one in there. This has an enable signal. I don't need this one. I can make this, I can remove the enable from there. And I can enable the read enable. Okay. Address. Make this for my output. instead of having the clock signal going into a gate, that's a bad practice. So perhaps, let's see what happens if I delete this. I really want my clock going directly to them to avoid any delay. So that's cleaner. Probably remove this from here. Put it right here so it looks cleaner. Probably remove this bus from here. Add a multiplexer. Make this 4 bits. Put my value on the bottom one. Fit this one back. And then I can probably put a AND gate right here. And another AND gate right here for my write enable. So when this is 1, this is gonna get routed. And I have my write enabled to both of them. But then my decoder is the one that gets to select which AND gate goes too high. And I think that should be it. Yeah, that looks right. I got my address. You can select between both. Let's see. See if it works. Okay. So if I want to put 00 on the first address, so 00, I want to write 00, so write enable, disable, and then I want to output that 00, so it works. If I want to output 3, I click read enable, and it works. Um, yeah, and that works. That works how I want to. And the good thing about putting it like that is right now, if I want to put the line in high impedance, I can easily do it with my read enable, and it will put the line in high impedance. So that is working perfectly fine. So this is a RAM of 4 bits. That's exactly what I needed. So now that we have implemented this RAM, um, this is our RAM for our CPU. Obviously, we want something bigger. So Logisim already provides our RAM. So if we make the address by 24, the data bit 32, we have a huge RAM that we can use to our advantage. We can feed it 24 bits. It's 24 bit, that's the limitation for Logisim. That's the address. This is the input, 32. That's the size of the world, of the word. We have a clock signal that we can use. We have a write enable that it will just exactly what we need to implement this, and an output enable. So if I output enable the first value, so we have an output out in the outside. If I want to move to the first, then I go here, and if I want to write some data in there, then I write enable. I clock the system. I disable write enable, and it'll keep that information. So if I want to output address 3, 0, but if I want to output again address 1, then I have to select my new address, then clock the system, and it outputs that. If I disable this, it'll keep it in there. So this is what we need for our system. So this is the RAM, and I hope you enjoy it. If you learned something, go ahead, hit a like and subscribe. Hope to see you in the next video.